Chapter 13, Lesson 3. In this lesson we'll talk about something called colligative properties. And essentially these are the properties of solutions as compared to the original solvent. And colligative properties will depend on how much the number of particles in the solution and not the kind of particles. This is very similar to what we talked about in the gas chapter, where no matter what kind of gas you have, we treat all gases the same. They all follow the same laws exactly the same way. So that's what we'll do here now with solutions. And we'll talk about these four areas: the lowering of vapor pressure, the raising, elevation of boiling point, the depression or lowering of freezing point, and then something called osmotic pressure. These first three we'll take a look at in this first lesson. So the first one will be vapor pressure. If you recall, vapor pressure is the pressure that the gaseous form of the liquid takes. Every liquid actually releases gases into the right above the liquid, and we can talk about the pressure that in a closed container, if you close it off, the pressure that's exerted by those gases. And anytime you have a solution, like in the case on the right, the vapor pressure actually decreases, and you can kind of see that by the fact that there are less particles in the gas phase here than there are here. And you can think of it as the solute particles, the dissolved substances, in this case the red balls, actually keep or bond with some of the solvent and keep it from going into the gas phase. That's kind of a rough way of understanding it. So the vapor pressure of the solution is lower than the original pure solvent. And this is the case essentially with anything that you dissolve. And here it says non-volatile solutes. So we're dissolving things that are not easily vaporized in general. And there's a lot to go along with this. The law looks like this, takes the form of a PA, this is the pressure of substance A, equals the XA, we call it the mole fraction. This is the mole fraction of your compound, and then the P naught A. And this little naught just means the original. Think of it that way. This means your original vapor pressure. So you take the original vapor pressure and you multiply it by the mole fraction. Now this is important because this is the mole fraction of the solvent, not the solute, not what you're putting in solution, but what was the solvent, what is doing the dissolving, what was in the solution to begin with. This is actually a very important point, and we'll do a little example of this here to solidify that concept. And here it is. Calculate the mass of propylene glycol, C3H9O2, that must be added to 0.340 kilograms of water to reduce the vapor pressure by 2.88 torr at 40 degrees Celsius. And the vapor pressure of water at this temperature is 55.3 torr. So the idea here is we'll use this equation. The pressure of A equals the mole fraction of A times the original vapor pressure of A. And recall A is our solvent, and in this case our solvent is good old water. So what we have to do is consider first, it says we're going to reduce the vapor pressure by 2.88 torr. So our final, let's find out what our final pressure would be. Our original pressure here is given to us as 55.3 torr. So this is 55.3 torricellis. And so we want to know the reduced pressure, so we can simply subtract the two. So we do 55.3 minus 2.88. And if you do this simple calculation, we should get a fine value of, make sure we do this properly, 52.4. We'll do 4.2 just in case. Torrs. And so what we're asking to do here is solve for the mass of propylene glycol that must be added. What they're referring to essentially is the mole fraction. We have to go through mole fraction. Remember that mass and moles are connected together. So we first have to rearrange the equation to solve for your mole fraction, your x of A. So let's do that on this side, and then we'll go to the next page to finish it up. So rearranging this, we'll have to divide the pressure on this side. We get ourselves the mole fraction of A equals the pressure of A over pressure naught of A. And because we have both of these values, let's plug them in and let's see what our mole fraction gives us. So mole fraction will equal 52.42 over 55.3. And in this case, we get a mole fraction of, if you do that calculation, we should get ourselves, let's go for 4 sig figs. How about 0.9479? And essentially this is our mole fraction. So we've only come halfway to the end. This is going to be a problem that's a little extensive. And so on the next page we'll continue on. Now we're adding 0.340 kilograms of water. That's how much water we have. And the question is, how much of this substance do we add to it? So we're going to have to undo this idea of mole fraction on the next page. So we got 0.9479. is our mole fraction of A. So this is what we have to work with. Now, if you recall, mole fraction is defined as the moles of A, in this case, divided by total moles, or the moles of A and whatever other substance. Now, in this case, our A is our solvent, recall, which is in this case water. So, what we're saying is we know how much water we have. In fact, in the problem, it says that we have 0.340 kilograms of water. So we have 0.340 kilograms of water. So we can actually find out how many moles of water we have. And then the total moles, this portion here, is actually moles of A plus moles of our other substance, which in this case is propylene glycol, C3H9O2. So what we'll have to do is plug in our unknown values and then rearrange to solve for the equation. So let's go ahead and first convert our kilograms of water to moles of water. Now we know that 0.340 kilograms is actually 340 grams. This essentially is just multiplying by 1,000, and then we can convert this to moles. We know that a mole of water is 1802 grams of water. So converting from grams to moles, 340 divided by 1802 gives us 18.87 moles of water. So this is essentially the value that will go up in the top portion of our mole fraction. So here's how our equation will be set up. Our mole fraction is let's try that again. Our mole fraction, we can do this in a second color, is 0.9479, and that equals the moles of water, which in this case, so we can put moles of water, H2O, divided by moles of H2O and moles of C3H9O2 is the idea. So in this case, we've got ourselves 0.9479 equals, our moles of water is 18.87 divided by 18.87 plus, essentially what we're going to be solving for is this value. So let's call this guy y, just to differentiate from x, which is used in the idea of mole fraction, so plus y. So what we'll have to do essentially is solve for y in this equation. And the way we'll do it is we'll first multiply the denominator over to this side. So we got ourselves this picture, 18.87 plus y multiplied by let's try that again, 0.9479 will equal 18.87. And so if we distribute, we should get ourselves, we're going to multiply 18.87 by this number first, 0.9479. This gives us 17.88 plus 0.9479y equals 18.87. Now to solve for y, we'll move 1788 to the other side. So we get 18.87 minus 1788, and that gives us 0.99. So 0.9479y is 0.99, and then we can solve for y by dividing both sides. So y equals 0.9479, 1.04. Now recall, this is moles of our propylene glycol, so this substance here. So it's asking us, the question asks what mass of it must be added. So all that we have left to do is convert from moles to grams, and this is again C3H9O2. So finally, let's finish the problem here by converting from moles to grams. 1.04 moles. A mole of propylene glycol is, since we have ourselves 3 carbons, that should give us 36.02 to be exact. We have 9 hydrogens, that's 909. We have 2 oxygens, that's 32 to be exact. So we have a total of, this is 11, carry the 1, 6, 9, 15, 16, 17, carry the 1, 77, 11. So we're going to be very close to about 78 here. Or actually 80 to be exact. So 80.5 grams. And here it is. We'll have to add 80.5 grams to 340 grams of water to lower the vapor pressure of water by 2.88 torr. Pretty extensive problem, but you can see how we've applied the original definition, and then the mole fraction definition to solve for it. Okay, going on to the other 2 colligative properties, the first being a boiling point elevation, the second being freezing point depression. We'll quickly talk about these and then do a calculation, and we'll finish the lesson. So here it says that these non-volatile solute-solvent interactions, meaning anytime you make a solution, you cause the solution to have a higher boiling point and a lower freezing point than the pure solvent. And this is true again of any solvent or any solute technically that you can put in the solution. So this is a way to see this is we took a look at this phase diagram from the last chapter, if you remember. And the phase diagram shows you the 3 phases, the solid, the liquid, and the gas. And the original phase diagram is here outlined. This is your original phase diagram, so you can know the boiling point at any temperature, any pressure you wish. And the whole point here is when you have a solution, the liquid range of the solution expands. So it's now a liquid at a higher temperature, and it's now a liquid at a lower temperature. In other words, your solution has a lower freezing point now and a higher boiling point. That's essentially the idea. And here this says this is the change in the temperature of freezing, and this can be calculated as the change in the temperature of boiling. The whole point is your solution has a wider liquid range now. It boils higher, it freezes lower. That's the whole point. And we'll take a look at the details of this on the next slide. So here is an equation for the boiling point elevation. And this portion here says that the change in the boiling point is equal to something called the Molality boiling point constant, Kb, multiplied by molality. Remember, this is molality, not molarity, and molality was moles per kilogram of solvent. And this is to distinguish it from molarity, in that molality is temperature independent. Because temperature is going up here, we don't want temperature to cause our solution concentration to change. That's why we are using molality here. And here are some molal boiling point constants for different substances. Famously, water's is 0.51. You can take a look at some other substances. There are some that are about 10 times higher than water. This is something called carbon tetrachloride, carbon tet, as we call it in the business. And so we can use any of these substances, and you can look up other substances as well. And here it says that the delta T, then the change in temperature, is added to the normal boiling point of the solvent. So this is just the change in the boiling point, not the new boiling point. A similar thing can be said and defined for the freezing point. So the change in the freezing point is freezing point constant times molality. And the previous slide actually had, let me go back to the previous slide, had a bunch of these freezing point constants as well, right? And these are the freezing point constants. So, putting them both together, we can actually do some calculations with them. And again, to re-emphasize, the delta T does not depend on what the solute is. You can put salt in there, you can put sugar in there, really any solute in water, and it depends on how many particles you have. So here's the problem before us. Calculate the freezing point of glycerol in ethanol. If this many grams of glycerol dissolves in 250 grams of ethanol. So, and they give us actually the freezing point and the freezing point constant here. So what we have is we have a solution not of water, but in ethanol. So this is our solvent here. And our solute then is glycerol. So we are dissolving glycerol in ethanol, is the idea. And we have this much glycerol, and we have this much ethanol. That's kind of the idea. So the equation set up for us is the temperature, the change in the temperature of the freezing point is equal to the freezing point constant times molality. So because the Kf is given to us, all we have to do essentially is find the molality, and then we can find the new freezing point. Now, molality, recall, is moles divided by kilograms. In our case, our moles will be moles of glycerol, that is our solvent, glycerol, and our kilograms will be kilograms of ethanol, that is our solvent. So, we'll essentially have to work with that, and we can do that calculation on the next page, seeing that we have a little space there. So let's go ahead and first find our molality. Again, molality is moles over kilograms, and then moles of our glycerol. So it looks like we're given 2.8 or 8.27 grams of our solute, of our glycerol. This is C3H8O3. And we'll have to first convert this into moles, because we're looking, remember, for the moles of this substance here. This is C3H8O3. Let's try that again. And so we'll have to put grams down here in a mole. Now, to total this up, we have 3 carbons. Each carbon is 12, so this is 36.03. Each hydrogen is 1, so we have 8.08. Each oxygen is 16, so we have 48 total there. To total this up, we have ourselves 11, carry the 1. We have ourselves 16 and 22, carry the 2. About 5 and 4 is 9, so we have 92.11 grams. So dividing these two numbers, 827 divided by 9211 gives us 0.0897978. Let's go ahead and go with 3 sig figs. Okay, and now this is our solute, and now we can take this solute and divide it by the kilograms of solvent. So we now can get the molality. Molality then is 0.08978 moles divided by kilograms. Now we saw that our mass of solvent, or ethanol, we had 250 grams of it. Ethanol. So this converted to kilograms would be simply dividing by 1,000, moving the decimal place 3 times to the left, and we get ourselves 0.250 kilograms. So we'll put that on the bottom, 0.250 kilograms, and we get a molality that looks like this. Essentially, we're multiplying by 4. 0.25. We get ourselves 3.591, or 0.3591, 0.3591 for molality. Now back to the original equation. The change in the freezing point is remember the freezing point constant times our molality, which in our case the freezing point constant is given to us as 1.99, and our molality is 0.3591. So what we're doing is we're decreasing by, let's put that in, 1.99 multiplied by 0.3591. We're given 0.7146 degrees Celsius, technically. Now the original boiling point we're given as, or freezing point in this case, for ethanol was given as the freezing point was negative 114.6 degrees Celsius. So now we have to add this. So recall that freezing point is decreased, so we'll have to subtract 0.7146 for a total of, and this will complete our problem, negative 114.6 minus 0.7146 gives us negative 115.3. Sig figs will go to the tens place because we're subtracting and adding, and this then is our final answer. Again, it took a little bit to get there, but we're finally there. So this will conclude lesson 3 of chapter 13.